Moving along in our discussion, we're going to be talking about next the Poisson distribution. So this is another discrete random variable, and I could just give you the PMF, but let's go ahead and go back to the previous video on the binomial random variable, and we're going to derive it from that, because this is really a limiting case of that, and first introduced to it, you should really think of it like that. So let's actually go right back to our previous example with the cars and the cities. So remember, if you didn't watch the previous video, the premise was there's this big city with a lot of cars, and they can either be red or white. Now in the previous video, I said that there's an equal chance of being either red or white, because there's an equal number of red cars, equal number of white cars. Now let's say that we're going to change that up a bit. What we're going to do is, if you remember, we had, let's say, some random variable x sub b is distributed binomial NP, where n was the number of trials we're seeing, and p is the probability of success, and that's when we're going to increase our count by 1. Now what we're going to do to get to Poisson is we're going to take n and let it go to infinity, and we're going to take p and let it go to 0, but not just arbitrarily. We want the value, we're going to call it lambda equals np, we want this product to stay constant. So that means that even though n is getting really, really big and this probability is getting really, really small, close to 0, even though that's happening, when you take the product, they're still kind of averaging in a sense, in that the magnitude of their difference is canceling out, so that this product remains constant at lambda, and this lambda is the same as the lambda parameter here, as we'll see in just a second. Okay, so going back to our cars example, what we're going to see is that we're going to observe a lot of cars, a huge number of cars. So we're just going to assume that this is a high traffic city first of all, and you're going to, instead of maybe there's a traffic cam sitting there, it's going to be observing cars all day long. Okay, so it has a huge, very large size of its sample. And let's say p is really small. So let's say instead of half and half, the probability of a white car is 0.0001. So there's barely any white cars in the city, but if we look long enough, we're going to find one. So now we see kind of where this is arising, the need for this limiting factor. Because if we didn't send n to infinity, if n was just some moderately small number, say it's still 10, if p was 0.00001, whatever I said, that small number, it's pretty likely we're not going to see a white car, because we're only observing 10 cars. But if we send n to infinity, then it's unclear if we're going to see a white car, because even though the probability is small, we're observing so many that, maybe we'll see one, maybe we won't. So to kind of capture that information, we're going to pass from this binomial into its limiting Poisson. And I'm going to show you the process of how to do that right now. So let's recall the binomial PMF. Probability that this binomial is equal to some k. Remember, k has to be within 0 to n integer inclusive of either bound. It's going to be n choose k. It's going to be p to the k and 1 minus p to the n minus k. Okay, and that's going to be and 0 otherwise. And this is going to be if we have 0 is less than or equal to k, less than or equal to n, k is an element of the integers. Okay, so we had that from before. Now, what we're going to keep this quantity here, lambda equals np. I'm going to rewrite all these p's in terms of lambda over n. So here's what we're going to do. We're going to take this. I'm going to expand this binomial coefficient out as what it truly is. Okay. And now we have p to the k. What is p? P is lambda over n. So I really have lambda over n to the power k. And I have 1 minus p here, so this is really 1 minus lambda over n to the power n minus k. Okay, so this is starting to get ugly. And we're going to have to go through a little bit of algebra here to get through some of these things. But we'll do it. So I'm going to rearrange these in a suggestive way that's going to be nice later on. So we have here a lambda to the power k, lambda to the k over k factorial. Okay, and then we have n factorial here. We have over n minus k factorial here, and we have n to the k on the bottom here. So this will simplify in a second. And here, this term right here, we're going to split it up as, I'm going to rewrite this fraction so it's not 1 minus something. So it's going to be n minus lambda over n to the power of n, and then n minus lambda over n to the power of negative k. So all I've done here is I've written 1 minus lambda over n as n minus lambda over n. And we're taking this exponent and split it up into two different factors. Now we just need to do a bunch of limits, so we're going to be using some limit stuff here. So this we'll leave alone. Okay, this is going to be part of our final answer. We'll leave that alone. This let's do that right here. So this is going to be notice n factorial over n minus k factorial is what? That means we keep the extra terms on the top. So we keep the n minus 1. In fact, we keep all the way to the n minus k plus 1. So that is what this factorials become. And then on the bottom, we have k n's multiplied together. So n times n all the way to n. There's k of these. Okay, so I'll put k. And how many terms do we have on the top? We actually have this term, this term, this term. And if you count them all up, it turns out there's k of those terms as well. So we really have n over n minus 1 over n minus 2 over n, all the way to n minus k plus 1 over n. Okay? And if you see, what's the limit of these guys? So remember, if you have a limit of products, you can do the product of the limits. So it's really, what's the limit of n over n? That's 1, obviously. So it's 1. And what's the limit of n minus 1 over n? Now, so this 1 is inconsequential when n is huge. So this is, again, 1. And in fact, even this last one, what's n minus k plus 1 over n? If n goes to infinity, this minus k plus 1 becomes inconsequential, so this is, again, 1. So it turns out this whole limit right here, output goes to 1. This is very good for us. Now, another easy one to do right now would be this one, because if n goes to infinity, this inside part does what? Again, this lambda becomes inconsequential because lambda is a fixed, remember? Right here, it's fixed. So this n over n, that becomes a 1. And again, this k is some constant, not a constant, but we're going to keep k fixed during this because we're trying to do it for a fixed value of k for now. So it's 1 to the power of something fixed, again 1. So this is nice, this goes to 1, this goes to 1. This is more unclear because it's this same thing, this inside goes to 1, but this exponent goes to infinity. So it's kind of an indeterminate form. We're going to use L'Hopital's rule, and it should do. So here's how we're going to use it. So we're going to rewrite this guy as e to the n natural log n minus lambda over n. And why can I do that? Because e to the natural log something is just the inside part. So it's really n minus lambda over n. Now that to the power of n, which is exactly what we have here. So this is justified. Now I'm taking the limit of this as n approaches infinity. So I really want the limit of this as n approaches infinity. And once I get that limit, I'm going to take e to the power of that limit, and that'll be my total limit. Okay? So what's the limit of this? We're going to use L'Hopital's rule. So we have natural log n minus lambda over n divided by 1 over n. All I've done here is written this in a different form. Now I can use L'Hopital's, take the derivative of the top and bottom. Let me do that right now. So if we take the derivative of the top, we get n over n minus lambda. Okay, and we take the derivative of the inside. So that's going to give us what? It's going to give bottom, derivative of top minus top, derivative of bottom over bottom squared. All that over derivative of bottom. So derivative of bottom is negative 1 over n squared. Okay, so we can do lots of cancellations here. N minus n, these cancel, so we just have a lambda on the top. Here's the n, here's an n squared, so this n goes away. One copy of the n goes away there. Let's clean this up a little bit. So what we have is a lambda on the top. This negative 1 over n squared will come on the top as negative lambda over n squared. We have n minus lambda down here, and we have another copy of n. So really, here's that'll go away with this. So let me flip over, because this is getting a little messy. So let's see what we have. We have negative lambda n over n minus lambda. Let me write that. Negative lambda n over n minus lambda. Now it's a little bit easier to see what's the limit of this as n goes to infinity. We see that this negative lambda on the bottom is inconsequential as n goes to infinity, so it's really negative lambda n over n, which goes to, this limit is equal to negative lambda. And don't forget, we need to take e to the power of this guy. So it's going to be e to the negative lambda. So we see this guy goes to e to the negative lambda. So in all, what do we have? Lambda to the k over k factorial, e to the negative lambda. Nice, pretty clean, right? So e to the negative lambda, lambda to the k over k factorial. This is the PMF of the Poisson distribution. So let me go ahead and write that. So probability. And now, remember, here we're doing xb. Since we have limited this to the Poisson, we're gonna use x, okay? Because we're gonna take this limiting PMF as just being the PMF of our Poisson lambda random variable. So probability that x is equal to some k is equal to this, and we're gonna do 0 otherwise. Just a general thing in probability, even if you don't know what's supposed to go here, it's a good idea to put 0 otherwise, because it's going to be something here. So let's try to figure out what this is. In the binomial case, we saw that k has to be between 0 and inclusive, and k has to be an integer. Now k still has to be an integer, and so it has to be between 0 and n was sent to infinity, so really it has to be something. We have to say k is an element of the set 0, 1, 2, dot dot dot, which means it goes on forever because k n was sent to infinity. So we can choose any integer that is 0 or bigger. Okay, cool. So this is our law, and this is how we derived it. So it's actually really nice to see how it's derived because you see what it truly is. It's a limiting of a binomial. Okay. Otherwise, if you just saw this, it doesn't really make much sense. Okay, so now that we have this, we can do what we did in the previous videos. We can find expected value, variance, MGF, and then look at a few other things. So let's find the expected value. So the expected value of this guy is what? So it's going to be the expected value of x. Remember, what this is defined by what? So this is defined as we need to take each value of this, so 0, 1, 2, so on. Not 0 because that'll just cancel, but 1, 2, every single positive integer. Multiply it by this. So that seems a little daunting at first, but not so bad. So it's going to be a sum from k is equal to 1 to infinity, right? Because we can choose any, n was sent to infinity, of, we have to multiply that number times the probability of that number happening. So it's e to the minus lambda, lambda to the k over k factorial. Looks a little scary, but let me show you how to work it through. K equals 1, infinity. This k cancels with one copy of the k down here, so really what we have left here is e to the minus lambda, lambda to the k over k minus 1 factorial. So already it's a little bit nicer. Now let's take this e to the negative lambda and a copy of this lambda out front. So I have lambda e to the minus lambda, sum from k equals 1 to infinity, and I'll put what's in the sum right below. So it's going to be lambda to the k minus 1 over k minus 1 factorial. Now notice this k minus 1 is kind of annoying. So since we started the sum at 1, we can just start it at 0 and replace this with k. So this is really sum k equals, well, out front we have lambda e to the minus lambda, k equals 0 to infinity of lambda to the k over k factorial. Now this guy, this sum right here, is, if you know the Taylor expansion for e to the power of x, this is exactly what that is, except here x is lambda. So we have equals lambda e to the minus lambda e to the lambda. And of course these guys, these two will just combine to become 1. So it's really cleanly just lambda. So even though it starts a little bit messy, it becomes something very nice. So the expected value of a Poisson distribution is just the parameter lambda. Now let's do the variance. That can get a little bit, now that we have this trick, it's not that bad. So let's try to do that. So the variance of x, remember, is the expected value of the random variable x squared minus expected value of x squared. This we already have. We know this is lambda squared. Okay. What is this? Expected value of x squared. We're going to do the same thing. It's going to be sum k equals 1 to infinity, and x squared will represent here by k squared, right? So it's going to be k squared e to the minus lambda, lambda to the k, over k factorial. Now we're going to see we're going to run into a little bit of a problem, but it's easily resolved. What are we going to do? So we're going to start off the same way. So we're going to have one of these k's will go away, we'll take out the beginning of this factorial. So we're going to have k e to the minus lambda, lambda to the k over k minus 1 factorial. Now notice we can't use the same trick we used up here because we have this extra k kind of just sitting here. So what are we going to do? Let me find another piece of paper. Okay, so what we're going to do about this, so what we're going to do is first we're going to take this e to the minus lambda and a copy of lambda out front. So we're going to do lambda e to the minus lambda, and we're going to, what's in the sum right now? It's k equals 1 till infinity of k lambda to the k minus 1 over k minus 1 factorial. And now we're going to rewrite this k as k minus 1 plus 1. So we're going to rewrite this as two sums. Really, it's lambda e to the minus lambda. It's going to be, the first sum will be k equals 1 to infinity, k minus 1, lambda to the k minus 1 over k minus 1 factorial, plus the next sum is k equals 1 till infinity of just 1. So lambda to the k minus 1 over k minus 1 factorial. Okay, I know this might be confusing. Let me explain. So I started here, and this constant stayed out front, and now I rewrote this k as, k equals k minus 1 plus 1, which there's no problem with that. And since I did that, I split this up into two sums, one that had this as the beginning and one that had this as the beginning term. So that's why in this term, everything else is the same, except this was replaced by k minus 1, and in this sum, everything else was the same as here, except I used the 1 and put it there. I didn't write it explicitly, but it's there. Okay, so now this is much easier to do. This is like we did in the previous ones. So we have lambda e to the minus lambda. Now see, this k minus 1 will go away with the first term in this factorial, so that we really have, and really this sum now starts at 2, because if you put 1, this is 0. So it's sum k equals 2 to the infinity, and then we have lambda to the k minus 1. Let me pull a lambda out front. So we have lambda to the k minus 2 over, and since these canceled, what we're left with down here is k minus 2 factorial, okay? And this is just what it is. Okay, this looks messy right now. Let's clean it all up and bring it all together. Okay, so this sum right here is just, it's the same as what we had on the previous sheet, actually, because if you look at this previous sheet, this sum that we had in the very end, it was a sum lambda to the k over k factorial, starting k equals 0. Now this is the same thing because we're starting k equals 2, so it's really just offset. So this is, again, this is just e to the lambda. And if you look, again, this is the same thing because it's offset by 1 instead. So this is just, again, e to the lambda. So we have e to the minus lambda, e to the lambda, e to the lambda. So they all cancel just to become 1. So this goes away, this goes away, this goes away. So we're left with nothing but lambda squared plus lambda. And this is equal, this is not the variance yet. Another thing in probability, you might do super long calculations to try to find expected value of x squared. Don't forget that you still have to subtract expected value of x squared, okay? So what I mean is that we've just found this. We need to subtract lambda squared. And it's a good thing we do because that makes it even cleaner. So this minus lambda squared gives us just lambda. So the cool thing about the Poisson distribution is that the mean and variance are the same, and they're the parameters. So they're very easy to remember. And you can just state them right off the bat, which is really cool. Okay? So here we have this, and last thing to find the moment generating function, which is not that bad. So expected value of e to the s x, we're going to do the same thing. We have sum k equals 0 till infinity, e to the s, let's do k here, and we're going to have e to the minus lambda, lambda to the k over k factorial. Okie doke. Now let's clean this up. So this is going to be sum k equals 0 till infinity. Let's pull lambda to the k, and this e will combine as e to the s. Actually, what we're going to do is that you see that this is e to the sk and this is lambda to the k. So we're going to combine this as let me just rewrite it again and then show that in the next step. So yeah, we have lambda to the k and e to the sk. So we're going to rewrite this as k equals 0 till infinity, lambda e to the sk. Okay, by the rules of exponents, I've just put them together. And this e to the minus lambda I'll pull out front. And again, it's over k factorial. Now look at what this is. In this previous piece of paper, we had that sum from k equals 0 till infinity of lambda to the k over k factorial was just e to the power of lambda. So it's e to the whatever is here. Now this is the same form, but it's not lambda that's in here. It's lambda e to the s. So it's actually e to the minus lambda. And now it's e to the power of lambda e to the s. Okay, it looks a little bit ugly. So let me actually just wrap around back here and write the final statement up here. So if we combine these, if we put the exponents together and add them, it's going to be e to the lambda e to the s minus lambda. And factoring this lambda out, e to the s minus 1. So the moment generating function of a Poisson distribution, this Poisson random variable, is e to the lambda, which is the parameter, and inside the parentheses we have e to the s minus 1. So be careful because this is e to the something eventually up here. So it's a little bit confusing, but just if you remember where this e to the s and the minus 1 is not applied to the s, it's applied to the e to the s. Okay, so if you know the derivation, it's easier to memorize what this guy is. Okay, cool. So I guess the last thing we'll do is draw a quick picture of what a typical Poisson distribution might look like. So here we have, again, the same. This is going to be drawing the PMF. So here's k. Here's probability that x equals k. So here's the graph of the PMF. So I won't put numerical values, but I'll kind of say when the parameter is small. So when we have lambda, let's say lambda equals 3. The shape generally looks kind of like, well, where does it start? We can say that when k is 0, what is this? When k is 0, 0 factorial is 1. Lambda to the 0 is 1. So just e to the negative lambda. So it starts at a place determined by this parameter. So it's just it starts somewhere, and then it's kind of skewed. Okay, so if we were to draw it, it would look a little bit like that. Okay, and each point represents a different integer value. Okay, so it's a little bit skewed like that. But if we have, for example, lambda equals 10, it looks a lot more like a normal distribution, or like the binomial distribution we saw previously, in that it kind of shifts over. So it kind of, let me do it in a different color even. So I'll do it in blue. So lambda equals 10 in blue. It kind of becomes a lot more looking like this. And if you put bigger values of lambda, it actually skews the other direction in that, for example, if you put lambda equals 100, now I shouldn't put this on the same graph as here, but just to show you the behavior, it has this really long tail on the left, and then it does the same behavior over here. Okay, so that's the interesting thing about the Poisson distribution. So I actually meant to show a few more examples of showing that the sum of two independent Poisson random variables is Poisson. But I think I'll do that in a next video or a side video. So actually, I'll make that side video. Click here if you want to see a few additional cool things about the Poisson distribution and Poisson random variables.